Yeah, thanks for the introduction. I will talk about planar site percolation vector embeddings. So first of all, I will briefly review what is a site percolation model. So the percolation model was first introduced by Broadbent and Hammersley. They originally introduced this model to consider the spread of fluids through a random medium. So the percolation model is defined on a graph. So a graph consists of a set of vertices V and a set of edges E. So each edge is just an ordered pair of vertices. So once we have a graph, we are going to define the percolation configuration on the graph. So each vertex could take one of the two possible states, either state 0 or state 1. Once we fix the state of all the vertices, we have a percolation configuration. So this is a site percolation configuration because each vertex has either state 0 or 1. If each edge has either state 0 or 1, we have a bound percolation model. Okay, so then a zero cluster in a percolation configuration is a connected component in which every vertex has state 0, and one cluster is a connected component in which every vertex has state 1. So once we have a percolation configuration, we just consider all the possible configurations on a graph. All those possible configurations form a sample space. And then we are going to define a probability measure on this sample space. So a probability measure is, so the most natural and most studied probability measure is called the i.i.d. Bernoulli P percolation model. So in this model, we associate an i.i.d. Bernoulli random variable to each vertex. So that means each vertex could have state 1 with probability P and state 0 with probability 1 minus P, and the states of different vertices are independent. Then the classical question in percolation theory is when do we have an infinite cluster? So we want to know when an infinite cluster exists. So if we understand this question in an intuitive way, when P is small, it is less likely that each vertex takes the value 1, and then the infinite one cluster is less likely. As we increases the value of P, and it becomes more and more likely to have an infinite one cluster because the probability that each vertex takes value 1 just increases. So the question is, when does an infinite one cluster exist? So indeed, this is the case. It is known that there is a critical value of PC. So whenever P is less than PC, almost surely there are no infinite one clusters. When P is greater than PC, almost surely there are infinite one clusters. So here is the simulation of set percolation on the two-dimensional square grid. In this case, each vertex is represented by a small square. So if this vertex takes value 1, then we color this small square by blue. If this vertex takes the state 0, we color that small square by white. Okay, and then, so in the first picture, we have a simulation for the i.i.d. Bernoulli percolation model on the two-dimensional square grid with P equals 0.25. So each small square has probably 0.25 to be blue and 0.75 to be white. And we see in this case, it seems that we don't have an infinite cluster. And we don't have an infinite blue cluster. We don't have an infinite one cluster. And in the middle picture, we simulate with P equals 0.35, and it seems that we don't have infinite one cluster either. And in the right graph, we simulate with probability equals 0.65. So it seems that in this case, we could have an infinite blue cluster. This is indeed the case because for the two-dimensional square grid, it is known that the critical percolation probability PC is equal to 0.59. So the first two pictures are subcritical case, and the right graph gives us supercritical case. There are infinite clusters, but in those first two pictures, because P is less than 0.59, so we don't have infinite clusters. Okay, so not only are people interested in the existence of infinite clusters, people are also interested in the number of infinite clusters. So to that purpose, people define different critical percolation probabilities. So the probability PC site is the inframe of OP, such that i.i.d. Bernoulli P set percolation has an infinite one cluster, and the PU set is inframe of OP, such that there is a unique infinite one cluster almost surely. From the definition, it is straightforward to say that PC is always less than or equal to PU, because if there is exactly one infinite cluster, then there must be an infinite cluster on the first hand. Then the question becomes when we have strict inequality, when PC is strictly less than PU, and when they are equal. So we may understand when PC is strictly less than PU is like there's an intermediate state where we have infinite clusters, but the number of infinite clusters is at least 2. So it is known that for quasi-transitive amenable graphs, PC is always equal to PU. So quasi-transitive means that there are only finitely many different types of vertices. Amenable means that the subgraphs could have a boundary as small as we want. So basically, if we take any finite subgraph, we consider the total number of vertices on the boundary of that subgraph divided by the total number of vertices in that subgraph, and we take the inframe over all finite subgraph. If this inframe is 0, then that means this graph is amenable. If this inframe is strictly positive, that means this graph is non-amenable. So examples of amenable graphs include like all the cubic lattice. So the graphs we consider that today are all amenable. In previous talk today are all amenable. So non-amenable graphs include, for example, the degree D regular tree with D at least 3. And then the number of infinite clusters. So the percolation model is an independent model. On certain dependent models, the number of infinite clusters on certain two-dimensional dependent models is also related to the uniqueness and the non-uniqueness of infinite volume Gibbs measures. For example, the Ising model and the diamond model and the random cluster model. So there are also examples when PC is strictly less than PU. So the simplest example is we consider a regular tree with its vertex degree D at least 3. In this case, PC is equal to 1 over D minus 1, and PU is equal to 1. We say that PC is strictly less than PU in this case. And then in the highly influential paper by Benjamini and Schramm in 1996, they asked the question, does PC strictly less than PU for all non-amenable quasi-transitive graphs? So there are a number of spectacular results towards partially solving this conjecture under some additional conditions, but despite all those results, this conjecture remains open. So I'm not going to details, but what I'm going to discuss today is a related conjecture. So these are two related conjectures in the same paper by Benjamini and Schramm. Those two conjectures also consider the number of infinite clusters, the existence of infinitely many infinite clusters. However, they do not assume quasi-transitivity. On the other hand, they assume planarity. So a graph is planar, means that it can be joined into the plane, with vertices represented by points and edges represented by continuous curves, such that any two edges cannot intersect at a point which is not a vertex. So these two conjectures says that, first of all, suppose G is planar and the minimum vertex of G is at least 7. Then for every P in the range PC set to 1 minus PC set, there are infinitely many infinite one clusters. Moreover, the conjecture is PC set is strictly less than 1/2. So this interval is always non-empty. So the second conjecture says that if G is a planar graph, assume at P equals 1/2, almost surely percolation occurs, then almost surely there are infinitely many infinite one clusters. So ever since those two conjectures, a number of people have been working on this, and these two conjectures have attracted a significant interest among mathematicians. Now let me briefly review the history. Earlier work focused on the case when the graph is both planar and quasi-transitive. So in the year 1998, Lally has showed that infinitely many infinite clusters exist for certain values P in certain vertex transitive tilings of H2. Indeed, he started the side percolation on fusion groups. And then in the year 2000, Benjamin and Schramm, they showed that if G is a transitive non-amenable planar graph with one end, then 0 strictly less than PU, PC strictly less than PU, strictly less than 1. So this is for both bound and side percolation. And if the G plus is a dual graph of G, that means the planar dual graph. That means that each vertex of the G plus corresponds to face of G, and two vertices in G plus are joined by an edge. If and only if the corresponding faces share an edge, and they show that this PC of G plus PU of G dual graph is equal to 1 for bound percolation. And then in the year 2016, Lyons and Paris, they generalize this result to quasi-transitive graphs. They show that if G is a quasi-transitive non-minimal planar graph with one end, PC of G plus PU, the dual graph of G, is equal to 1. So the difference between transitive and quasi-transitive. Transitive means that there's only one type of vertices. Quasi-transitive means that there are only finitely many different types of vertices. So if there's only one type of vertices, that means any two vertices can be mapped to each other by a graph automorphism. And quasi-transitive means that there are only finitely many different types of vertices. So we can find a finite set of vertices such that any vertex can be mapped to one of those finitely many vertices by a graph automorphism. Okay. So then people began to think about the conjecture without the quasi-transitive assumption. So it was proved in 2020 that infinite connected planar graphs join a plane without accumulation points. Basically, that means any compact set of the plane intersect only finitely many vertices and finitely many edges. So infinite connected planar graphs of vertex degree at least 7 have PC set strictly less than 1/2. And then in 2022, we can prove these two conjectures under the further assumption of quasi-transitivity. This is by a correspondence between bound and side percolation. And then we can prove the first conjecture, which assumes that a planar graph with vertex degree at least 7, when this graph infinite connected properly embedded into the plane. So properly embedded basically means without accumulation points. And so this latest result does not assume the quasi-transitivity. So it's basically, I think it solves the first conjecture I was talking about. So now let me briefly review the main ideas in solving this. Now let me briefly talk about the main ideas in solving those two conjectures. So for quasi-transitive graphs, one can adapt the argument of Benjamini and Schramm for bound percolation to side percolation and show that if we consider S0 is the total number of infinite zero clusters and S1 is the total number of infinite one clusters, and the pair S0, S1 could only be 0, 1, 1, 0, or infinity, infinity. And then we can show that PC of G plus PO of G star is equal to 1. So G star is the matching graph of G. So the matching graph, G star contains G as a subgraph. So the vertex set of G star is exactly the same as the vertex set of G, but two vertices in G star are joined by an edge, if and only if they share a face. So if not all the faces are triangles, so G star contains G as a proper subgroup because the edge set of G is a proper subset of edge set of G star, if not all the faces are triangles. Okay, so, and then also PU of G plus PC of G star is equal to 1. When G star is the matching graph and G is one-ended.
So if G is the triangulation, then G equals E star?
Yeah. Yeah, so this shows that if a triangulation and if it's a triangulation and if PC is equal to PU, then PC must be 1/2. Okay, then from this, we can see that PU is equal to 1 minus PC of G star. But because G is the subgraph of G star, so PC of G star is less than or equal to PC of G. That means 1 minus PC of G star is greater than or equal to 1 minus PC of G. Okay, so then in the interval PC to 1 minus PC, that means that's a subinterval of PC to PU. And then in that interval, we must have infinitely many infinite clusters. Because S0, S1 must be either 0, 1, 1, 0, or infinity, infinity. In that interval, we have both infinite zero clusters and infinite one clusters, and then in that interval, we must have infinitely many infinite zero clusters and infinitely many infinite one clusters. So without the quasi-transitive assumption, a lot of existing techniques can no longer apply. For example, in the quasi-transitive graphs, it is known that the total number of infinite clusters can only be 0, 1, or infinity. But without quasi-transitive graphs, without the quasi-transitive assumption, this is no longer true. So it could be with positive probability that the number of infinite clusters could be an arbitrary finite integer. And also, the ergodic theorem does not hold anymore. So so it is known that in quasi-transitive, with the quasi-transitive assumption, so those events that are invariant under the automorphism of the graph, those events always have probability 0 and 1. And without the quasi-transitive assumption, you don't even have automorphism group, and you cannot say that what is an automorphism invariant event, and their probability is always 0 and 1. You cannot say that. And also, the mass transport principle does not work anymore. So then, without the quasi-transitive assumption, we need basically new idea to solve conjecture 1. What we did is we explicitly construct embedded trees on such graphs. So as we have already seen, the properties of percolation is closely related to the structures of the graph. So now let me briefly review the definition on the graph structures. So a graph is called planar, means that it can be drawn in a plane. Vertices are points, and edges are continuous curves, and any two edges cannot intersect at a point which is not a vertex. Transitive basically means that there is a subgroup of the automorphism group such that all the vertices are in the same orbit under the action. Quasi-transitive means that there's a subgroup of automorphism group, so all the vertices are infinitely many different orbits under the action of gamma. If a graph is amenable, that means if we just consider any finite subset of vertices, and we consider any finite subset of vertices, we consider vertices on the boundary divided by the total number of vertices. And then we consider the inframe of this quotient over all the finite subgraphs. If this inframe is 0, then we call the graph amenable. If this inframe is strictly positive, it's called non-amenable. So this IV of G is called the trigger constant. So the examples of amenable graph include all the hypercubic lattice CD. Examples of non-amenable graphs include like the regular tree with vertex degree at least 3. Then the number of ends of connected graph is like we remove a finite subgraph, and then we count the total number of infinite exponents. And then we consider the supreme of this total number of infinite components after removing a finite subgraph. And this supreme is taken over all the finite subgraphs. And this is called number of ends. So examples of one-ended graph include all the hypercubic lattice CD with D at least 2. And if we consider a line graph, so vertices are represented by integers, and edges are represented by lines joining consecutive integers. So this is an example of two-ended graph. And then if we have a regular tree with vertex degree at least 3, this is an infinitely ended graph. And the G star is the matching graph. So this is a graph obtained from G by adding an edge between any two vertices sharing a finite phase. I also want to mention that we'll consider side percolation on a properly embedded planar graph with vertex degree at least 7. This graph is always non-amenable. Okay, so what we are going to do is we are going to construct embedded trees on such graphs. So here is an example of a 7 regular triangulation of the hyperbolic plane. So this is the vertex transitive graph. Here, every vertex has degree 7, and every face is a triangle. And then we consider an embedded tree, which is represented by the right graph. And so the gray graph is the 7 regular hyperbolic triangulation. So we can say that for this tree, at the root, we have the root vertex has degree 2. So the root vertex here has degree 2, and all the other vertices has degree 3 or 4. And in this tree, we know that the critical percolation probability PC of a tree is the reciprocal of the average branching number of this tree. For this graph, because its average branching number is strictly greater than 2, so its critical percolation probability is strictly less than 1/2, because this tree is a subgraph of this 7 regular hyperbolic triangulation. So in this gray graph, the critical percolation probability PC is less than or equal to that of the tree is less than 1/2. So indeed, our first result says that if I have infinite connected planar graph properly embedded in R2, again, properly embedded means that its join into the plane has no accumulation points, such that one of the following two conditions holds. First one, the minimal vertex degree is at least 7. Second one, the minimal vertex degree is at least 5. And the minimal fifth degree is at least 4. Then we can find an embedded tree whose root vertex has degree 2 and all the other vertices has degree 3 or 4. And this tree is indeed a subgraph of G. So each vertex of this tree is also a vertex of G, and each edge of this tree is also an edge of G. Okay, so the existence of embedded trees on a non-amenable graph with large trigger constants is not new here. So indeed, in the year 1997, Benjamini and Schramm, they show that if G is a locally finite graph with trigger constant at least n greater than or equal to 1 is an integer, then G has a spanning forest such that every tree in the forest is isomorphic to Tn plus 1. Here, Tn plus 1 is a tree in which the root has degree n and the other vertices has degree n plus 2. This is a general theorem which applies not only for planar graphs, but any non-amenable graph with trigger constant at least n. However, if we want to apply this theorem to our case, we want to construct an embedded tree whose PC is strictly less than 1/2, then we need n to be at least 2. If n is at least 2, then G should be a locally finite graph with trigger constant at least 2. But if we assume that G is properly embedded planar graph with vertex degree at least 7, its trigger constant could be less than 2. So we cannot directly apply this theorem because the assumption is too strong. Moreover, the proof of this theorem uses flows on the graphs, which is abstract. It's not immediately clear what's the geometry of this embedded tree. What is the geometry of this embedded tree? And it's not clear how to use this theorem to prove the exponential decay of two-point connection probabilities. So what I'm going to talk about is a more explicit way to construct embedded trees on properly embedded planar graph with vertex degree at least 7. So we have a root vertex V. It has two neighbors, V0 and V1. And we assume, so the root vertex, we could choose any vertex to be the root. Any vertex could be the root. The root has two children, V0 and V1. And we assume that V0 and V1, those two edges are in the same phase. And then starting from V0, we assume it has again two children. And then we assume that the edges V0, V0, 0, and edges V0, V01 share a phase. And then we assume that working along V0, V0, 0, we have exactly 3 faces on the right. And then this point V1, it has 3 children, V1, 0, V1, 1/2, and V1, 1. And we assume that working along V1, V1, 1, it also has 3 faces. It has 3 faces on the left. Then from V0, 0, we construct a tree isomorphic to the tree rooted at V0. From V0, 1, we construct a tree isomorphic to the tree rooted at V1. From V1, 0, we construct a tree isomorphic to the tree rooted at V0. And from V1, 1/2, we construct a tree isomorphic to the tree rooted at V0. And at V1, 1, we construct a tree isomorphic to the tree rooted at V1. Okay, and then this way, we have some subgraph, but the question becomes why this subgraph is a tree, why those paths we constructed do not cross each other and form a cycle. And in order to show that this is indeed a tree, we will define a discrete curvature at each vertex. So the discrete curvature is defined to be 2i minus sum over all the faces incident to a vertex, the degree of that face minus 2 divided by the degree of that face, multiply pi.
Sorry, I missed something. Can you tell us what the hypothesis on the original graph is? It's just a planar graph of degree at least 7?
Yeah, it's so in this picture, it's a planar graph with no accumulation points and the vertex degree at least 7. Yeah.
At least 7.
Yeah, it could also be, so in this picture, it has vertex degree at least 7. It could also be vertex degree at least 5 and fifth degree at least 4, but the construction is a little bit different, but you can still construct an embedded tree with critical percolation probability strictly less than 1/2. Okay, so you define such a discrete curvature, and then if either condition 1 or condition 2 holds, so condition 1 is vertex degree at least 7, condition 2 is vertex degree at least 5, and fifth degree at least 4. If one of those two conditions holds, and then we have negative curvature at every vertex. So using the negative curvature assumption, we can show that any cycle must satisfy this inequality. So then that means if we have n vertices, n adjacent vertices, and the left-hand side from a path, and left-hand side is greater than the right-hand side for any first two vertices, first three vertices, and up to first n vertices, the left-hand side is also greater than the left-hand side, then this is self-forwarding path. It can never form a cycle. Okay, using this, we can show that the subgraph we constructed is indeed a tree. Okay, then it follows immediately whenever P is between PC of this tree, 1 minus PC of tree, there are infinitely many infinite 1 clusters, and also infinitely many infinite 0 clusters. However, this tree is a proper subgraph of G. That means PC of G is strictly less than PC of T. Okay, then it remains to show that when P is between PC of G to PC of T, there are infinitely many infinite 1 clusters. And when P is between 1 minus PC of T and 1 minus PC of G, there are also infinitely many infinite 1 clusters. It remains to show that. So first, let's consider a case when P is between PC of G and PC of T. In that case, we will first show the exponential decay of two-point connection probabilities. So we consider two vertices U and W. We will show that whenever P is less than 1 minus PC set of T, the probability that U and W are joined by a path consisting of all state 1 vertices is less than or equal to e to the power negative Cp. So Cp is a constant depending only on P, but independent of U and W. Multiply the distance of U and W in the matching graph of U and W. So how do we show this? So what we are going to do is we're going to consider the shortest path in the matching graph joining U and W. And along this shortest path, we will construct a number of disjoint doubly infinite trees separating U and W. So such that the number of those doubly infinite trees are disjoint and their number increases linearly with respect to the star distance of U and W. And then if U and W is joined by a 1 path, it must be joined by a 1 star path. If they're joined by a 1 star path, then in now this doubly infinite tree, there should be a doubly infinite 0 path. But when P is less than 1 minus PC set of T, that means 1 minus P is strictly greater than PC of T. So in each of these doubly infinite trees, there is a strictly positive probability that there exists a doubly infinite 0 path. And therefore we get the exponential decay because if we want none of them have a doubly infinite 0 path, in each tree, the non-existence of such a doubly infinite 0 path is strictly less than 1. And those trees are disjoint, so the probability that none of them have a doubly infinite 0 path would be less than some number less than 1 is less than some number less than 1 to the power of the number of those trees, but the number of trees grows linearly with respect to the star distance of these two vertices. Okay, this is how we get this exponential decay. We also need to understand exactly what is PCG. We also need a characterization of this PC. So what this PC really is. So there is a characterization when the graph is transitive. So the critical value of PC is characterized by the average number of vertices on the boundary of the box that is joined to the center of the box by a 1 path. So basically, if this number is less than 1, so the average number of vertices on the boundary of the box joined to the center of the box, if this average number is less than 1, then it's subcritical. If it's greater than 1, then it's supercritical. We can generalize this characterization to any infinite connected locally finite graph without a transitive assumption. The difference is in the transitive case, every vertex is the same. But without the transitive assumption, so different vertices are different. So what we need is some kind of an epsilon delta language, something like this. So this PC is a supreme of those average number of points on the boundary of the box that are joined by one path to the center of the box. If this number is less than 1, then it's subcritical. If this number is greater than 1, then it's supercritical. So the major difference is in the without the transitive assumption, different vertices could be different. Then for each epsilon positive, for each p greater than pc, we're going to define a set of vertices vp epsilon. So vp epsilon consists of all the vertices such that if we just consider the number of vertices on the boundary of the box, average number of vertices on the boundary of the box joined to the center of the box, this number is greater than or equal to 1 minus epsilon for any finite box containing this vertex as an interior vertex. And then we can show that for each p greater than pc of G, such type of vertices is always infinite. And then using differential inequalities, even the technical differential inequalities, we can say that whenever P is such a vertex, the probability that P is in an infinite cluster is bounded below by the same constant. This constant is independent of this vertex. It depends only on epsilon and this P greater than PC. So this is same positive constant. And then there's another critical percolation probability defined by Schramm, so this is called P connection, which is the supreme of P such that the 2-point connection probability decays to 0. And then from what we have shown, we have already shown that when P is less than 1 minus PC set, the 2-point connection probability decays to 0. So this is less than P connection of G, but we also know that PC set of T is less than 1/2, so this is greater than 1/2. And we consider A1 to be the event that there is a unique infinite one cluster. And we use BKR inequality and FKG inequality. We show that the probability that U and V are joined by a one path is bounded below by probability that U is in an infinite one cluster multiplied the probability that V is in an infinite one cluster multiplied the probability that there is a unique infinite one cluster. So those events are not increasing, but we can still show this by the BKR inequality, which does not require the events to be increasing. Okay, so then we can just consider when P is between PC set of G and P connection of G, and we choose both U and V to be in that set VP epsilon. And then because this VP epsilon has infinitely many vertices, so we can choose U and V be in that set and let the distance of U and V go to infinity. Because P is less than P connection of G, so when the distance of U and V goes to infinity, the left-hand side is 0. But because both U and V are in VP epsilon, so the probability that U is in infinite cluster and the probability that V is in infinite cluster are bounded below by the same constant independent of U and V. And then as a result, the probability that there is a unique infinite one cluster has to be 0 whenever P is between PC set and the P connection of G. Okay, so then because with probability 0, there could be a unique infinite one cluster, then with probability 0, there could be finitely many infinite clusters. Because if with positive probability there are finitely many different clusters, by the finite energy, we can somehow modify the configurations on finitely many different vertices, and we can obtain that with strictly positive probability, there's a unique infinite one cluster. Okay, so then we could show that whenever P, so because with probability 0, there are finitely many infinite one clusters, but P is greater than PC site, that means there almost surely there exists infinite clusters. So the number of infinite clusters has no choice but to be infinite. So whenever P is between PC site of G and 1 minus PC site of P, almost surely there are infinitely many infinite one clusters. Okay, so we have shown the left part. So we want to show that whenever P is between PC of T to 1 minus PCA of t, there are infinitely many PCA of g. So this goal is to show this. There are infinitely many infinite clusters. What we have done is we have shown that P is in PCA of t, and 1 minus PCA of t, there are infinitely many infinite clusters. And we have also shown that when P is between PCA of g and PCA of t, there are infinitely many infinite clusters because PCA of t because PCA of t is less than 1/2, we show that P is less than 1 minus PCA set of t. There are infinitely many infinite clusters. So we have already shown this part and this part. It remains to show this part when P is between 1 minus PCA set of t and 1 minus PCA set of g. There are infinitely many infinite clusters. So if we use planar duality, we use planar duality because here there are infinitely many infinite one clusters. We can show here infinite one clusters have infinitely many ends. But that basically means that after removing a finite subgraph, the number of infinite clusters could be as many as we want, but this is still not exactly infinitely many infinite clusters. So what we are going to do is, this is still not infinitely many infinite clusters. This is still not exactly infinitely many infinite clusters. We need to split the infinitely many ends to infinitely many infinite clusters. So we first show that assume that there exists finitely many infinite one cluster, but those infinite one clusters have infinitely many ends. Then we show that with positive probability, with strictly positive probability, at one vertex, the infinite star cluster has exactly one end. Then we just consider C and E to be the total number of n-step non-self-touching polygons passing through E, and we take the nth root of this C and E and take the limit slope as n goes to infinity, somehow like the exponential growth rate of the n-step non-self-touching polygons. We call this gamma G of E, and we show that if 1 minus P is less than inframe over all the edges, 1 over gamma G star of E, then the probability that each edge is in a non-self-touching zero-star polygon of length at least m, as m goes to infinity goes to 0, then the probability that there is a one-ended infinite zero-star cluster at V0 is 0. Then we show that, then we verify this condition, PCA site of G star is less than the inframe of all over all edges of E, 1 over gamma G star of E. If every face of G is a triangle, then it follows directly if every face of G is a triangle and P is between 1 minus PC set of G star minus delta, 1 minus PC set of G star, there are infinitely many infinite one clusters. And if not all the faces are triangle, we can add actual edges in faces to make every face to be a triangle. Then we may consider this triangular graph with those actual edges as a graph with higher percolation probability for this this original graph with no those actual faces. So we can just consider a mixture of bound and set percolation model. So we make those bound to be present with probability 1, and those bound to be present at probability 0. So this is indeed a percolation model with higher P. This is the percolation model with lower P. So it is known that if a percolation model with higher P with infinitely many infinite clusters, then the percolation model with lower P also have infinitely many infinite clusters. So this is by a uniform percolation argument, again by Schramm. So basically, the uniform percolation means that so if P is above PC, and then we consider any vertex and consider above center that vertex with certain radius, and then we let that radius go to infinity, eventually that ball will intersect an infinite cluster. And then we consider the probability that the ball intersects the infinite one cluster in the i.i.d. Bernoulli P set percolation. And then if this probability converges to 1 uniformly in all different vertices, then we call that the uniform percolation. Okay, and then with the uniform percolation assumption, we have whenever in the high-level percolation P2 there are infinitely many infinite clusters, then in the low-level percolation P1 there are also infinitely many infinite clusters if percolation ever occurs in P1. That means if in P1 there are infinite clusters, then there are infinitely many infinite clusters. So in general, uniform percolation is not an easy condition to be checked, especially when P is close to PC. But recall that what we are going to do is when P is relatively large, it's much larger than PC. And then we have an embedded tree. Instead of using the original version of uniform percolation, it considers the intersection of a box, of a ball with the infinite cluster. We can consider the intersection of the embedded tree with the infinite cluster because our P is always greater than PC of T. Okay, so we can consider the subtree of depth n. And as n goes to infinity, the probability that this tree will intersect an infinite cluster, of course, converges to 1 uniformly because all those trees are isomorphic. And P is greater than PC of T. And this also removes, if we use this tree version of uniform percolation, this almost also removes the bounded degree assumption here because those trees already have a fixed vertex degree. Okay, and then, a weaker version of this theorem was also proved, and for the assumption of quasi-transitivity and unimodularity. And then we're done with the proof that whenever P is between PC of G and 1 minus PC of T, there are always infinitely many infinite one clusters. Then I still want to mention a special case when uniform percolation holds. So this is called the semi-transitive graph. So semi-transitive graph is, again, a generalization of quasi-transitive graph. So that means it has a finite set of vertices such that any other vertex, we can find a vertex in VF, such as Y is mapped to X by an injective graph homomorphism, no longer automorphism, but injective graph homomorphism. Okay, so all the quasi-transitive graphs are semi-transitive graphs. And semi-transitive graph will always have uniform percolation whenever P is greater than PC. And with the help of that, we can see that for a semi-transitive graph, PC set of G star plus PU set of G is equal to 1. For one-ended semi-transitive graph properly embedded into the plane with minimum vertex degree at least 7. So based on what we have already done, it remains to show that at the critical percolation probability, here, when P is equal to the critical value of PC, and the probability that there is a unique infinite one cluster is equal to 0, again, by the inequality we have already shown. So this is bounded above by that. But assume we have infinite one cluster. Assume this is strictly positive. Then we just consider Y is one of those finitely many vertices, and the minimum of all such Y's, such as the probability that Y is in an infinite cluster, is bounded below by a positive constant. But U and V, the connection probability always decays to 0 exponentially with respect to distance in the matching graph. So the left-hand side is 0, the right-hand side is PPA1 multiply a positive constant. So this PPA1 has to be 0. So then we can show that when this graph is semi-transitive, one-ended and probably embedded into the plane with vertex degree at least 7, then PC set of G star plus PO set of G is equal to 1. That's all I want to talk about. Thank you.